So, as a mechanical engineer, whenever I've tried to get into computational fluid dynamics, I've only really been given one of two options. Either A, buy a copy of ANSYS, or B, torrent a copy of ANSYS. Now, what if I told you that there's actually a third option, wherein you can achieve similar results, if not better, through just open source software? Well, that's what we're going to look at today. So basically, there will be 6 main steps in performing a CFD simulation. We'll briefly be walking through them in this tutorial. Timestamps for each section can be found in the description down below. Firstly, before we can apply CFD to a problem, we first need to define our problem. In this tutorial, we'll be looking at a very crude wind tunnel simulation studying the flow of air around a car without turbulence. To do this, we first need to create a CAD model that defines a flow field. Next, we discretize said flow field with the help of a meshing tool. After that, we run the simulation on the mesh. Finally, we visualize the simulation results. We'll be using FreeCAD, Gmsh, OpenFOAM, and MPICH for this. Although all 4 main tools are very popular individually, I really wasn't able to find a single tutorial covering an end-to-end simulation. And you know what they say, if you can't find a tutorial doing exactly what you need, make a tutorial doing exactly what you need. First, let's take a quick look at all the steps involved before we jump into the performance. These are the steps we'll need to do in FreeCAD. These are the steps we'll need to do in Gmsh. In OpenFOAM, we'll be using the icoform solver for now, with MPI for parallelization. And finally, these are the steps we'll be doing in Paraview. So now that that's out of the way, let's get started. We start off by hopping into the image workbench, where we snap the 3 views using the create planar image in the 3D space tool to snap our front, side and top views into frame. After aligning the 3 views to the screen, we hop into the sketcher workbench, where we trace an outline of the 3 views using the spline tool. After sketching the 3 views out, we jump into the part workbench again, where we extrude the 3 sketches and we take their intersection to end up with our final car. Now that we have a rough car model over here, the next thing we do is we place it inside our wind tunnel, and then we take the difference of these two objects to get our flow domain. Finally, we export the flow domain as a step file. Step file for meshing in Gmesh. Next, we import the step file into Gmesh. So now that we have our object imported into Gmesh, what we first need to do is we need to define physical groups in our geometry. First up, we add a volume over here, and then we go about by adding each of our surfaces to the mesh as well. So let's first define our inlet, outlet, wall, and finally our car. So in Gmesh, you actually have a couple of options with regards to what kind of mesh you can generate. So you have a tetrahedral mesh, a quad mesh, or a hexahedral mesh. So we'll try generating a hexahedral mesh for now. And now that our surfaces have already been defined and our global mesh size factor has been set 2.2, which is the value we're taking for our case, let's toggle mesh visibility so that we have only 2D faces visible for now. And let's start by generating our mesh. First, we click on 1D to get the 1D mesh generated, then 2D to generate the 2D mesh, and then 3D to generate the 3D mesh. So we can visualize the mesh using a clipping layer, and by sliding it along, we can see that our flow field, which is not being covered up over here. So yeah, our mesh has been generated pretty normally. We can also toggle the 3D elements and 3D faces as well if we want to look at that. We can also check that out in the clipping layer, and that will also give us a better idea of what each flow element looks like in our mesh. So now that that's out of the way, all we need to do is export the mesh, Ctrl E, and we'll save our mesh to our case. We'll call it flowfield.msh, and make sure that we're saving it as a version 2 ASCII file for OpenFOAM reasons. We're not saving all elements, we're not saving any parametric coordinates, we're just saving the mesh. Now that that's done, let's get along with the OpenFOAM stuff. So let's take a look at our case setup. we can do that by running the tree command. Now this tells us that we have initial conditions, we have our constants folder, and we have a systems folder. We also have an instructions.md document, which is, as the name suggests, the instructions for running the simulation, and we have the flow field mesh which we exported from Gmsh. So to figure out how we run the simulation, let's just read the instructions. Alright, so this tells us to first generate the mesh using the Gmsh to form command, and then it tells us to check the validity of our mesh using the check mesh command. So let's do that first. Now that our mesh has been generated, let's check its validity. And yeah, our mesh has been generated successfully. So next up, let's look at the next step in our instructions. Next step was to run decompose par to run a simulation in parallel. Now let's do that. Alright, so our flow domain has been split up to run on our two CPU cores because I have a dual core processor. So we specify the number of processes down here in the decompose par dict, which can be found in our system folder. Alright, so next up we need to start running our simulation. We can do that as follows. Alright, so to run a simulation, we're just going to use this command. Core count, we're replacing it by 2 because I'm running a dual core processor, and 2 is the number of cores which I had specified in my decompose par dictionary. Now, if I let this run, it'll start running the simulation. So now that the simulation's finished running, let's merge the simulation results using reconstruct par. Now that that's finished running, we can finally view our simulation results in Paraview. We open Paraview using the Paraview command. Alright, so in Paraview, let's first open up the control dictionary. And use the OpenFOAM reader. Alright, so now we can see our simulation results have successfully been imported into Paraview. Let's give it solid color for now. Surface. So now that we've got our simulation into Paraview, let's take a quick look at the velocity profile at a particular cross-sectional slice. To do that, we hit slice on this, and let's hit apply. So over here we can see that so over here we can see that initially the field looks a little bit random, but if we run it forward in time, we can see that a wake is forming slowly behind the car, which reaches out behind it. So yeah, that's how you run a quick, simple open source CFD simulation. I hope you enjoyed that video. Sorry if it was a little bit too rambly in a couple of places. This is my first time making a walkthrough tutorial of sorts. And yeah, all the best for your open source projects. Feel free to reach out in the comment section down below if you have any questions. I will be attaching the code files for this entire case setup and with the instructions on my GitHub, and a link to that will also be provided down below. All the best. Bye.